The decimal number system is what we've grown up with, what we've been using our entire life, where everything is based on a power of 10. When we count, that's what we do. And we largely started counting probably when we were very little using our fingers or our toes, and since we have 10 of those, it was very convenient for us to think in terms of powers of 10. The decimal number system uses base 10, and as we progress through this lecture, we will talk about other bases that can be used to represent numbers. So in the base 10 number system, every digit is given a certain value, and you have, if you remember your place value from elementary school, your ones place, your tens place, your hundreds place, etc. Off to the other side of the decimal point, you've got your tenths, hundredths, thousandths, etc. And so those are negative powers of 10 to the right of the decimal, and to the left of the decimal you have your positive powers of 10. And your available digits in the decimal number system are 0 through 9 inclusive. And we can generalize the idea of a base by saying that for all bases you can use the digits between 0 and n minus 1. So in this case we have base 10, n minus 1 being 9. Our available digits are 0 through 9, and each of our places are powers of our base, powers of base 10. So we can actually use any integer 2 or greater as the base of a number system. Your text, I think, may refer to this as the radix of a number system. And the available digits, as I mentioned, are 0 through n minus 1 inclusive. So for example, if you had the base 6, every place to the right of the radix point would be a negative power of 6, and every place to the left of the radix point would be a positive power of 6. And we're now going to refer to it as the radix point rather than the decimal point, because decimal point implies base 10. So if we were operating in base 6, our first place to the left of the radix point would be our 6 to the 0 power, or our ones place. Then we would have our 6 to the 1s, or 6's place, and 6 to the 2s, 36's place, etc. And our digits that we could use, 0 through n minus 1, would be 0 through 5. How do we notate bases? Well, because we're going to be using binary and hexadecimal and decimal in this class, we're going to make sure that we use a subscript in order to represent a different base. So that way there's no confusion about whether a number is in binary or hexadecimal or decimal or various other number systems. So we will talk about those bases in just a moment. So if you had 12 base 3, that would be 1 times 3 to the 1 plus 2 times 3 to the 0. So in decimal, 12 base 3 would be 3 plus 2, which is 5. 25 base 10 would be the standard 25 that we've been used to our whole lives, so that is in base 10. So the binary number system is what computers use, largely because, as we mentioned in the previous lecture, computers are very good at distinguishing between voltage levels. And so they can set something as high or low. They're not terribly good at discriminating between different levels and getting into analog voltage without doing a conversion first. So it's very easy for these switching circuits that we're going to be dealing with to actually distinguish one voltage level as high and another as low, and to process that very quickly. And in order to do that, we use the binary number system, which is base 2. And so in base 2, the only digits that are available are 0 or 1. And so if you have a low voltage, it gets processed as a logic 0. If you have a high voltage, it gets processed as a logic 1. And depending upon what your digital system is, the different voltage ranges will be selected accordingly. And as we mentioned, in a lot of systems, nominally logic 0 is 0 volts or ground, and nominally logic 1 is 5 volts, although some systems operate off of 3.3 volts or other voltage levels. This is very nice because it's very easy to represent electronically. So if you think about those transistors as being switches, switches are either open or closed. And so in that case, we can clearly define the switch is either open or closed, 1 or 0. And so as we use those transistors to discriminate between different voltage levels, they can represent different numbers. So we can actually put together several different switches, several different bits, and they can be used together to represent different numbers. So how do we count in decimal? Well, in decimal, you count 0 through 9, and then you have to add another place. So you may have remembered as a child, you count from 0, 1, 2, 3, all the way up through 10, and then when you run out of fingers, you might have counted with your toes or had to make a notation on a sheet of paper or something like that. That represents a carry out to the next place. And so in decimal, we keep adding until we get to that 9, and then carry out to the next place. And when the digit reaches 9, you know that the carry will happen and it'll go back to 0, and the next place will advance by 1. In binary, we do something very similarly, but in that case, remember the base only has available digits 0 and 1. And so in this case, we count 0 and 1. There is no 2 in base 2, so once we get beyond 1 and we would count up to 2, we have to carry over to the next digit and then 0 out the first. So if we were to use 4-bit binary, our first value 0000 would represent 0, then 0001 would represent 1. So what would come after that? Well, you'd have to carry out, and so you would have 001, and then you would 0 out on the rightmost bit there. So it would be 0010, and then you would have 0011, 0100, etc. So some terminology that's used in binary. Every binary digit is referred to as a bit. And if you group together 8 bits, that's a byte. If you group together 4 bits, that's a nibble. I think whoever came up with this nomenclature must have been in need of a snack. Must have been around lunchtime when they came up with this idea. And there's also a least significant and most significant bit. So the rightmost bit is your least significant bit, and your leftmost bit is your most significant bit. And that's all about place value. The bit that is furthest to the left is given the highest power of 2 that's available. The bit that's furthest to the right is typically your ones place, and it has the least significant place value. And usually our systems are restricted in terms of how many bits we have available, and that's usually governed by the architecture of our system or what our software can handle. And so most digital systems are either 8, 16, 32, or 64 bits. And so that tells us how large a number we can represent with that particular number of bits. So modern operating systems happen to be 64-bit, and early microprocessors were only 4-bit. So we've advanced quite a bit in terms of the values that we can represent, in terms of the number of addresses in memory that we can write to and read from, and we'll talk a good bit more about that later. So some other binary terms: when you have to carry, as you would in regular mathematics, that adds 1 to the next digit, and then you add 1 to the following digit. Well, when you end up needing to carry out from your most significant bit, and there is not another place to put that, that is called an overflow. And so if you have a value, let's say you have 8 bits. Well, with 8 bits in unsigned binary, you can only represent between 0 and 255. If you were to add 1 to that, you would have the value 256 in decimal, and we cannot represent that with simply 8 bits. And so an overflow indicates that you have a value that is bigger than you can hold. You may have experienced that on a calculator. If you put in a value and you're adding things and it gets to be bigger than the calculator can represent, or bigger than a spreadsheet can represent, you end up with an overflow. A carry or borrow is exactly the same as it is in decimal arithmetic. So if you're needing to subtract and you don't have enough in your place value where you are currently, you can actually borrow 1 from the more significant neighbor next door and then bring that on down and subtract from it. So here are some examples. If we wanted to convert a binary value to decimal, what we need to do is just look at where all the ones are and look at the corresponding power of 2 and then multiply them together. So in our example here, we have 1 in the 2 to the third place. That's over here, the most significant bit. Then we also have a 1 in the 2 to the 1's place. And we have zeros elsewhere. So if we multiply this and add them together, you've got 2 to the 3 is 8, plus 2 to the 1 is 2. So 8 plus 2 is 10, and then we'll just put this subscript 10 to indicate that that is now in base 10, or our decimal number system. So you can at this point pause the video and practice converting these binary values to decimal. And we're back. What values did you get? Okay, for 1100, that should be 2 to the third, you have a 1, and 2 to the second, you have a 1, so that would be 8 plus 4, so that should work out to 12 decimal. And 0110 should be, you have 2 to the second and 2 to the first, so that's 4 plus 2, that is 6. And then 1111 has a 1 in all of our 4 places there, so that's 2 to the third plus 2 to the second plus 2 to the first plus 2 to the 0. So 2 to the third is 8, plus 4 is 12, plus 2 is 14, plus 1 is 15. So there's a couple methods that we can use to actually take decimal and convert it to binary. One method is the way that I was taught when I was going through a class similar to this, and that is to actually go through and find the most significant power of 2 that is less than or equal to that particular number, and put a 1 down there. You know, that is the most significant place that you need a 1. Everything to the left of that will automatically be zeros. And you'll go ahead and subtract that power of 2 from your original number that you're trying to convert. And then you're going to look for what you need in the remaining bits to the right to represent that remaining value. And you'll continue comparing those values to the next power of 2, the next power of 2, until you find another power of 2 that can be subtracted. And you'll keep doing this all the way until the remainder is 0. And once you get down to 0, you can just fill in everything to the right with zeros. So as an example, let's look at 200 decimal and see if we can convert that to binary. Well, if we start looking at our powers of 2 and writing them out, we have 1. Well, that's certainly less than 200. 2, well, we might need to consider that. 4, 8, 16, 32, 64, 128, also still less than 200. Then we get up to 256. Well, that's too big. So we know in the 256 places we're going to have 0. And then our 1 is going to be in the 128 place. And then we need to figure out what is going to go in these other places from the 64's place on down to the 1's. So our largest power of 2 less than 200, 128, we know we're going to need at least 8 binary digits to hold our value there. And so we are going to subtract that 128 and have 72. And our current binary value puts a 1 in the 128's place. And at this point, we don't know what's going to go in the rest of our places. And so we have 72 remaining. And the next power of 2 is 64. Well, 72 happens to be greater than 64. So we're going to put a 1 in the 64's place, take 64 away from 72. And now we're down to 8. Now if we take that remaining value, 8 happens to be less than both 32 and 16, so we can go ahead and put zeros in both of those places. Now we've got our last 4 bits to fill in, and our next place happens to be 8. Well, 8 is less than or equal to 8, so we can go ahead and put a 1 in the 8's place. And so what we're going to do is fill that in, and now our remaining value is 0. Well, what does that tell us about our remaining bits? We have no value left to represent, so all those remaining bits need to be filled in with zeros to the right. And so our final value for 200 in decimal is going to be 11001000. And so we see that there. There's also another way, and this is how your textbook shows you to do this. You can actually do successive division by the base. And so if we take 200, divide it by 2, and we're going to do long division format here, so we get 100 with a remainder of 0. Then we take that 100, divide it by 2, we get 50 with a remainder of 0. And we follow on through 25, and then we get on to 12, and at that point we have a remainder of 1. And we keep going all the way until the quotient gets down to 0. Then what we can do is actually assemble the remainders in reverse order, starting at the bottom and putting them up in the top. And that actually works out to give us all of our powers of 2, just by assembling them in reverse order. So if you want to learn more about that, pages 9 and 10 in your book explain that particular method and why that works. So here's another opportunity to pause the video and do a little bit of practice and figure out how to convert 25 base 10 and 100 base 10, two decimal values, into binary. Okay, and we're back. 25 base 10. What did you get there? Well, in that case, you would have to take away a 16, and you would also have an 8, and you would also have a 1. So you would have 1s in those corresponding places, 0s in the other places. When you had 100, that is going to have the largest power of 2 less than or equal to 100 is 64. You take that away, you're going to have 36 left to represent. So you're going to put a 0 in your 64's place, and you're going to have a 1 in the 32's place, and you can figure out the rest from there. Just fill them right on in. Some notes on binary values. Most digital systems actually have groups of 4 for bits. And so typically you have 8, 16, 32, or 64. So we group our bits into nibbles. And so with 17, if we were to just represent that, you could have just 1, 0, 0, 0, 1. But because we like to group things in a group of 4, we will pad with zeros to the left to make 8-bit binary here. Hexadecimal is also quite commonly used in computer systems. This is nice because it allows us to represent each of those groups of 4 with just a single character. Why? Because every 4 binary places will actually be another power of 16. The problem with hexadecimal is that we don't have a simple way with just our numbers that we're used to of representing values greater than 9. And so what we do in hexadecimal is when we want to represent 10, 11, 12, 13, 14, and 15, we actually start using letters. And so for 0 through 9, it's the same as the decimal number system, but for 10 we use A, for 11 we use B, all the way up through F for 15. And our base conversion actually follows a very similar process. And so in this case, you look for the biggest power of 16 that's less than your value or less than the remainder after you've already taken some away. But in this case, you have one extra step. In this case, you want to know how many times can you take away that power of 16 from the remaining value. So for example, if you wanted to convert 2003 base 10 to hexadecimal or hex, then you would start by looking at your powers of 16. Well, you've got 1, 16, 256, 4096. Well, it's less than 4096, so we know we're not going to need a 16 to the 3's place. But we can take away more than just 1 256 out of this. So we'll have to figure out how many times 256 can go into 2003. And so, how many 256s can we take out of 2003? Well, the answer is 7 there, because 7 times 256 is 1792. 8 times is too much, so we're going to take 7 away, and then once we subtract that off, we know our first digit is the 7, and we have 211 yet to represent. And so if we look at our next power of 16, it's our 16s place, 16 to the 1. And the question is, how many 16s can be taken out of 211? And so the answer there is 13, because 13 times 16 is 208. That's less than that. The other power right next to it, 14, is going to be 224. So that's a little too much. So in this case, we're going to go ahead and take away 208 from 211, and we need to represent 13. The problem is we can't just put a 1, 3 down there, because that would be confusing as to whether we meant 13 or we meant for that 1 to actually be in the next place value. So we're going to use the character D for representing 13 in hexadecimal. So far we've got 7D, and then how many did we have left over? Well, we have 3 remaining, because we just took away 208, and so in hexadecimal we can simply just write that 3 on down. That's our last digit. So we have 7D3 in base 16, or hexadecimal, is equal to 2003 decimal. So here's a good way. Go ahead and practice this and see what you can get. Convert 234 to hexadecimal. Alright, binary to hexadecimal is actually quite easy to do. In this case, what we do is just make groups of 4, and if you don't have even groups of 4, you can pad with zeros to the left until you get a complete group of 4 on the left, and then just convert each of those 4-bit clusters into hexadecimal digits. So in this case, 1100 would work out to 12. 12 we represent with C. Then you have 1001 is 9, and then 0011 works out to 3. The reason that works, as I mentioned before, every group of 4 bits represents a power of 16. So in this case, your least significant bit of these 4 is your 1's place, 1s, 2s, 4s, 8s. This least significant bit within this cluster of 4 is your 16's place. Then you have 32, 64, 128. Here's your 256's place. That happens to be 16 squared. And then if you keep going on out, you'll see progressively larger powers of 16 at every least significant bit inside of the 4-bit clusters. Octal is not used quite as much as hexadecimal, but that's also favorable because it allows us to group 3 binary bits together, and then we can do a similar procedure to allow us to convert things into base 8. Binary coded decimal is another way that people use binary to represent numbers. And so in this case, instead of converting the whole value to binary from decimal, you just convert each digit. So in binary coded decimal, if you had 728, you'd find the corresponding equivalent binary for 7, and then tack that onto the corresponding binary equivalent for 2 and 8, and you'd get what you see there by putting together 0, 1, 1, 1 to represent 7, 0, 0, 1, 0 to represent 2, and 1, 0, 0, 0 to represent 8. So the binary coded decimal equivalent, or BCD, is what you see there on the screen. Binary arithmetic is very similar to the arithmetic you're used to. The main difference is that when you have a carry out, that happens with groups of 2 rather than groups of 10. So in this case, if we add starting on the right, 1 plus 1 would be 2, but we can't write down 2 right here. That doesn't exist in binary. So we put a 0 and we'd carry the 1. And now we have the 1 that we carried in plus 1. That's also 2. So we write down 0, carry the 1. 1 plus 0 is 1. We didn't have a carry this time. 1 plus 1 is 2. So we write down 0, carry the 1. And then we have 1, 0 plus 1, 1, 1 plus 0, 1, and 1 plus 0 is 1. And so in this case, if we were to have a carry out here, we didn't have that right here, but if we were to have a carry out right there, that would be an overflow, which would mean we didn't have enough bits to represent our answer properly. But in this case, we do have enough bits. We can represent that sum so we don't have to worry about carryouts in this particular example. Gray code is another way that people use binary, and in this case this is quite nice if from counting from one value to the next you don't want to change but one bit at a time. So in this case you choose a sequence of binary values so that going from one to the next you only change exactly one bit. And so in this case you can start with 0, 0, 0, 0, and if you go to the next place, this would represent 1, and notice the least significant bit is the only one that changed. And then normally we would go up to 2, but in that case, if we were to switch from here to there, both of the least significant bits would have to change. So if we swap some values around, now we can make 0, 0, 1, 1 represent 2, and in this case all we're doing is changing this bit. And so this is one example gray code where if you go through the whole sequence, you'll notice that every time you go from one value to the next, only one bit changes. Then when you get to 1, 0, 0, 0 and rotate on back through, you'll notice that you have only changed from here to over there by one bit. So it is in fact circular. Well, thus far we've only been talking about positive values and we've only been talking about integers. So now let's talk a little bit about how we might represent negative numbers. Well, in the decimal number system, whenever we want to represent something as negative, all we have to do is tack a negative symbol onto the front. And so that is one approach that is sometimes used in binary systems. And so with that, what you do is just designate a bit as your sign bit, S-I-G-N, sign, to indicate whether something is positive or negative. And that's called a sign magnitude representation. So in this case, you can think about that sign and the magnitude being like a vector. And so the sign bit tells you which direction you're going in, whether you're going towards the positive end or towards the negative end. And then the magnitude tells you what value you're going. So you might have in the magnitude 8, and that could be either positive 8 or negative 8, and your sign bit represents that. And so in sign magnitude representation, you use the most significant bit, that is the leftmost bit, to indicate whether it's positive or negative, and then you use the remaining bits to indicate what value it is that is positive or negative. So if it's positive, you put 0 there. If it's negative, you put 1. So here's some examples. If you had positive 124, you would have a 0 in the sign bit followed by the corresponding binary for 124. If you wanted to make that negative, all you do is flip your sign bit to a 1. And so here's another opportunity for you to do some practice and figure out what value is represented there. So you might want to pause and work that out. Okay, and we're back. So in this case, we see a 1 here, so that indicates that something is negative. And how much is this place worth? Well, this is our 64s. And then down here, we've got our 2s, so this is negative 66. Well, in this case, this is positive. This looks easy. That's 0. So we have positive 0. Okay, good. Now what do we have here? Well, this is negative 0. So what's the difference between positive and negative 0? That's very strange. Well, the one downfall of sign magnitude representation is it actually allows us to have both a positive and a negative 0 value. And so effectively, because we have two different representations for the same value, it ends up wasting one particular value. And so there are other approaches to representing negative numbers where there is only one 0 value. So one approach is using the ones complement. So in this case, if your value is positive, it's represented exactly the same way as you would in the unsigned binary that we worked on before. Your leading most significant digit here will be, most significant bit will be a 0 if it is positive. But if you want to represent negative numbers, you simply compute the ones complement by inverting every one of your bits. So ones become zeros and zeros become ones. And in this case, when something is negative, you can tell right away because the most significant bit will be a leading 1. So here's an example. If we wanted to represent 14, positive 14 in 1's complement, we simply convert it straight to binary and leave it alone. Here's 8-bit 1's complement, and we're representing 14. If we wanted to represent negative 14, well, we can start out with our positive 14 representation and simply flip all the bits. And so now we have 1, 1, 1, 1, and followed by 0, 0, 0, and 1. This system also has 2 ways to represent 0, because you can have all zeros, obviously representing zeros, and then if you complement all of those bits, you now have negative 0 with all 1s. So both the sign magnitude representation and the 1's complement allow us to have both a positive 0 and a negative 0. One other notation, and this is what is most commonly used by computers and other digital systems to represent positive and negative numbers, is the 2's complement. So the 2's complement is very similar to the 1's complement in that positive values are exactly the same as unsigned values, just the same as positive 1's complement values. But to make a negative value, you first start with the 1's complement, that is, flip all the bits, and then you add 1 to the 1's complement. The nice thing about this is it actually solves the problem of having multiple zeros. Because if you had 0, you flipped all the bits to 1, and then you add 1, it's going to end up going back to having all zeros. And so this actually extends the range of values that can be represented by one value. Now, we have talked about how to represent positive and negative integers. Well, of course, that's not nearly all the numbers that we might want to represent with a digital system. So in addition to integers, we want a way to represent fractional values, or values that are after the decimal point. And so, if you remember, in the decimal number system, we had tenths, 100ths, 1000ths, etc. And those are progressive negative powers of 10. And so in binary, the pattern is very similar, and we have progressive negative powers of 2. 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, etc. And so, if we wanted to convert fractional values into fixed point binary representation, it follows from the first procedure that we talked about for converting values into binary from decimal for whole numbers. Well, you can do the whole number part. Go ahead and get that, represent that, then put down your radix point, and then for the part to the right of the decimal place, we want to go through a similar procedure where we're going to look for the largest power of 2 that is less than or equal to what we have left to represent. And so then we will put a 1 down in that place and subtract that from what we have to represent. If we don't have a match with the power of 2 that we're comparing, we'll put a 0 on down. And so we'll place that and put corresponding 1s and 0s in every place until you have as many places after the radix point as you desire. The problem is we can't just always put an infinite number of places after the radix, because we start running out of places in digital systems. And so there's a bit of a trade-off in terms of how much precision you can have. So here, let's go ahead and do an example. If you wanted to convert 0.376 decimal into binary, well, we can start by looking at our negative powers of 2. We've got 0.5, or 2 to the negative 1, 0.25, or 2 to the negative 2, 0.125, 2 to the negative 3, etc. Well, 0.376 is less than 0.5, so we would put a 0 in our place immediately to the right of the radix point, and it is greater than 0.25, so we're going to put a 1 in the 0.25's place. So our first two digits must be 0.01. Once we take away that 0.25, we still have a 0.126 left to represent. And so we see that 0.125 happens to be less than that. So we can go ahead and put a 1 in our next place. And now we have 0.001 left to represent. And so we can continue that process on out. We would know that our next digit would be a 0, and then we would continue getting several zeros until ultimately we would find another 1 to put in some bits later. Just as we did successive division to figure out binary values for whole numbers, we can do successive multiplication to figure out the fractional portion. So in this case, you can continue to multiply values by the radix. In this case, that's going to be 2, and then keep any value that ends up being greater than 1. So if you have a 1, that means you're going to put a 1 down in that place. That's the next digit. And then you're going to throw away that whole part and just keep going until you have as many digits as you desire. So let's do our 0.376 example again. If we multiply 0.376 by 2, our whole value here is still 0. So our first place after the radix is going to be 0. Then we take what's remaining, that 0.752, multiply that by 2. In this case, we do have a whole number part here, and so that will be our next bit after the radix, and we have this 0.504 left there. So we'll take the 0.504 and multiply it by 2. That does in fact give us 1.008, and so we'll put down 1 as our next digit, and then we're going to take that 0.008 and multiply it by 2. That gives us a leading 0 there. We take that 0.016, multiply it by 2. We still have a 0, and we can keep going following this same pattern and put things together. So if we wanted to have 8 places after the radix, this 0.376 would be represented. In this case, we put things together from top to bottom as 0.0110000. And so we can put that together, and it actually would follow on with several more zeros. But if you did this about 4 more times, you would see that, or actually 2 more times. If you multiply by 2, it'd still give you another 0, but then you multiply by 2 again, you'd see another 1 show up a little bit later on down the line. The way that a lot of modern day digital systems represent floating point values is they actually use the IEEE floating point standard. And so this was a way to actually standardize how non-integer values were represented. And the IEEE is a good organization for electrical and computer engineers and computer scientists to work together to develop standards for electronics. And so if you want to work with most systems, you should be using the standards that the IEEE has designated. This happens to be one of them. So to represent a floating point value using their standard, you actually have 3 different components that you need to compute. One is very easy. It is the sign bit, as we previously represented with sign magnitude numbers. So if you have a negative value, it ends up with a 1. If it's a positive value, you end up with a 0. Then you have the mantissa, which happens to be a fractional value in the range of 1 up through any value less than 2. We'll talk about how to compute that in just a moment. And then you have the exponent e, which actually multiplies your mantissa by 2 to the e. So let's look at how we can compute that. Well, first of all, you start by converting the value to fixed point binary. So for example, 25.3, if you were to work that out, this 1101 is 25, because that's 16 plus 8 is 24 plus 1 is 25. And then you'd put your radix point, and if you tried representing that 0.3, you would see you would get 0, 1, 0, 0, 1, 1. And this pattern actually continues on out. 0, 0, 1, 1, 0, 0, 1, 1. Then what we want to actually do is convert this to scientific notation. So if you remember, in scientific notation, typically you've written something with one value to the left of a decimal point, and then you have the decimal point and you carry it on out to however many places you want, and then you multiply that by 10 to a particular power. In this case, our scientific notation is not going to use the power of 10, but rather the power of 2. And so really, we're just going to figure out if we were to move this radix point so that we only had one leading 1 over here, how many places would we have to move it? And so it works out that it happens to be 4 places we would have to move it. And so in this case, once we have it in this form, we now know what the sign bit is, and we can pull out the mantissa and the exponent. So in this case, we have to look for our 1 sign bit, our 8 bits for the exponent, and 23 bits for the mantissa. And so if we go back here, our exponent is going to be this 4 value here, and our mantissa is going to be the binary value that appears after the radix point. We're going to put this such that our leading value happens to be a 1 every time, and then whatever happens to show up after the radix is going to be the value of the mantissa. So in this case, we have, if we're doing 32-bit representation of the IEEE format, we have 8 bits to use to represent the exponent and 23 bits used to represent the mantissa. In some programming languages, we also have what are called doubles or double precision values. In that case, we get still 1 sign bit, but now we have 11 bits to use for the exponent and 52 to use for the mantissa. So that allows us to represent some larger values and also to have more precision on the values that we represent. So in our example, we have a positive value, so s goes to 0. Our power was 2 to the 4th, and so in order to allow us to represent negative numbers for our 32-bit, we will actually add 127 to that value. So in this case, our exponent could actually have been negative, but we had a positive value. So what we will do is add 127 to our 4, so our E value happens to be 131. And if we convert 131 into 8-bit binary, this is what we get here, because this is 128, plus 2 is 130, plus 1 is 131. Our mantissa is what appears in our scientific notation after the radix point. And so we notice we had this particular pattern, and it repeated after a while to 0011, 0011, and we actually carry that all out to 23 binary places. And so if we wanted to put this all together, we put our sign bit, followed by our 8 exponent bits, followed by our mantissa bits. And so in this case, this is a 32-bit floating point representation for the decimal number 25.3. So this is how your computer would represent 25.3. If you're trying to put a value into, say, Windows Calculator or into an Excel spreadsheet, this is how it would represent that value that has something after the decimal place. In rounding, when you're working in traditional decimal, you may remember a rule where if the next place would be 5 or greater, you round up. Otherwise, you round down or just truncate. In this case, if the next digit would be a 1, that is when we will round up. Otherwise, we will just truncate or round down. Also, with binary and with digital systems, we can actually represent other characters like using the ASCII system. And so we want to represent more than just numbers. If we wanted to represent letters, we wanted to represent special characters like the $, pound sign, @ symbol, colon, semicolon, all our punctuation, spaces, and also some special non-printable things like end lines that tell us when we should go to the next line in a text file. We can represent all those things using ASCII. And so if you go to this website, www.ascii-code.com, you can see the different binary values that are used to represent your text. And so this way, if you're sending a file to somebody else, they can read it. No matter who designed your computer, all of the letters and numbers and special characters are represented using a standardized system. So you can see that at ASCII-code.com.